Let's talk a little bit more about polarization and understand why different materials can be polarized. Now, this is important because it goes back to the idea of a neutral object being attracted to a charged object. So let's think about what's going on with this. Let's have a chunk of metal sitting on a surface where the itself is insulating, and we have our positively charged glass rod above it. Now, the presence of these positive charges polarize the metal. The negatives are attracted to the positives, and so we end up with negatives on the upper surface and positives on the lower surface. So we call this polarized. There is again no net charge on the metal, but one surface has one charge, the other surface has the opposite charge. Now, there is a net force in this case, and the reason for that is that when two charged objects are closer together, they have a bigger force. So even though the magnitude of these two charges is the same, the positive charges are further away. So we have two charged forces to think about here. We're ignoring gravity, we're ignoring the normal force. Just think about the forces due to charges. Because the negatives are attracted stronger than the positives are repelled, because the positives are further away, we actually get a net force that's up. Think if these were little bits of paper, that in fact maybe this net force up is enough to make that little bit of paper jump up. Now obviously paper is an insulator, it's not a conductor, and we have been talking about this up till now, polarization in metals. So next we'll try to understand what's going on in an insulator. But this basic idea that one surface ends up more negative, the other surface ends up more positive, that difference in distance gives you a difference in force so that you do get a net force, that will happen for both insulators and conductors. For an insulator, the electrons are not perfectly free to move, but we can actually distort the atom a little bit. And this is going to be called a dipole. And we're going to be coming back to this over and over again in the class, and it's usually going to be kind of a detail in most chapters. So when we introduce something like fields, it's okay, what's the field from a dipole? So we'll come back to this kind of once per chapter. So the idea of our dipole is that it is neutral. But when we put this atom in the presence of an external charge, it gets distorted. That these negatives, again the electron cloud, gets attracted to this external positive charge, and the nucleus is repelled. Now this doesn't rip apart the atom itself, but it means that it's no longer symmetric. It's no longer a sphere with the nucleus at the center. The electrons, on average, are a little bit closer than the nucleus. What that means is that again you have a net force. Because the negative electron cloud is closer than the nucleus, you actually have a slightly larger attractive force than you have a repulsive force. So you have a net force that is attractive. So now think about what would happen if we instead had an external negative charge. If instead we had an external negative charge, the electrons have a repulsive force, and the nucleus would have an attractive force. Well, in this case, which force is bigger? Again, the attractive force, since it's closer. So in the case where it's an external negative force, you still have an F net that is in fact that is actually attractive. So this is interesting that whenever you have an external charge and an atom like this that can be polarized but not ripped apart, it is always attractive. And that again reflects the fact that we saw that a neutral object was attracted to both glass and plastic rods. When we think about insulators, we think about them as this dipole model, that we can separate a little bit the positives and the negatives, but we're not actually ripping them apart. The electrons aren't completely free to move, but instead of the atoms all being little spheres, we can elongate them a little bit. Now, note a few things that this picture shows. One, that you can have different axes of alignments, but in each case, this line points back to your external charge. Second, your polarization is greater of the atoms that are or molecules, so be it, that are closer to the external charge than the ones that are far away. But note that you're still going to have a net negative surface here and a net positive surface here farther away. So even though the microscopic process of what's happening if you have an external object that's an insulator versus a metal and you have an external charge, those microscopically are very different processes, but in both cases you polarize a surface of opposite charge on the near surface, and on the far surface it's the same charge. And again, that will give you a net force that's attractive. So the final topic here is that we can do what's called charging by induction. So again, we're going to show this with an electroscope, so hopefully you've watched the video that explains how this works. Initially, we are going to have an electroscope here, and you can think of a person actually being in contact with the electroscope, touching it. And there's a couple of ways to do this. There's really 3 objects here, and depending on which one you bring in first doesn't quite matter. But we have a person who's touching our electroscope, and so that whole system is going to be neutral, the person and the electroscope. There's no net charge there, no excess charge. We then bring in an external charge, so for instance, a glass rod with positive charges. We don't make contact, we just bring it close to the electroscope. Now this is polarization, and we would see then that the negative charges from both the person and the electroscope actually come to be on the surface of the electroscope near that external charge. That leaves an excess of positive charges on the person and an excess of positive charges on the leaf. But note, just as this picture shows, many more positive charges, or excess positive charge, is on the person compared to the electroscope. Then what happens is the person stops touching the electroscope and backs away. Notice that they're taking some of the positive charge with them. Your positively charged rod still has not come into contact, but we remove that as well. So these excess negative charges here redistribute, and so 2 of these negative charges cancel out 2 of these positive charges, but we are still left with excess negative charge. So our leaves still repel, but notice what's happened here. We have actually created a net charge on our electroscope that actually never came into contact with our other charged object. Not only that, we have induced, this is called induction, so we have induced a negative charge on the electroscope when actually what we brought in was positively charged. So this is charging by induction. And again, it's a phenomena that if we didn't understand charge at a microscopic level and understand why charge can sometimes move and why it sometimes can't move, and the idea that we're always dealing with neutral objects which have both a mix of positive and negative, this wouldn't make any sense. So part of this is our historical understanding of charge.